So for a given bathroom break, what is the probability of using the jug? That will just be 0.25, like 1 over 4, because that's just the P for that one trial. And the second one, if she drives long enough to take 6 bathroom breaks, what is the expected value for the number of times she would use the jug? That will just be n minus p. So it will be 6 divided by 4, which is 1.5. And see what is the probability that out of the 6 times she would use the jug for 3 of them. So that will be 6 choose 3 and times 1 over 4 and like times 3. No, it's not times. How should I call that? Power 3. So wait, let me type. So I'm not very good at expressions. So basically, that is the Bernoulli function, right, Aubrey?
Yep.
Yeah. And so the D is a tricky one. So if she on average uses the bathroom 5 times per 12 hours of driving, what is the rate a lambda of jug uses per 12-hour shift? So lambda by definition will be the events happening during a certain interval. So that will be 5. Right? Am I right? So, and E, E is a tricky one. So the expected length of the trip is 9 days. So during this 9 days, with estimated 12 hours of driving per day, will she have to empty the jug? So basically, we need to calculate how many times she need to use the jug. So that will be 9 multiplied by 5, and then multiplied by P. That is equal 11.25, which is less than 12 times. So she will not have to empty the jug. And F is to use the Poisson, because it said was a probability that she will have to empty the jug twice. So the K being 2 here, K equals 2 and lambda equals 5. And if we use a Poisson function, that will be, the result I got is 0.08. Is it correct?
I'm still catching up here. All right, so the lambda is 5 times 1/4, so that's 5/4, 1.25. And then if we change the length of the trip to 9 days, it's 9 times 5/4, which comes out to 11.25. So no, she will not have to empty the jug. And then all right, let's see. So we're going to have to change that lambda to 5/4, 2e to the minus 5/4.
Oh.
Yeah. And what is that new probability?
Oh, okay. Right. Thank you.
Welcome.
Yeah. So that's divided by 4, I guess. So
Yes.
it's 0.02. Right? No. Sorry.
So let's see. Emptying the jug would be 24 uses and we have a lambda of 5/4.
I
So
thought the lambda was just 5.
so
And
5
she will
times,
use the jug 1/4 of the time.
yeah, she's not using the jug every time. So for 12 hours of driving, she would use the jug 5 times 1/4.
Okay.
Yeah, so that's the lambda per 12 hours. And then when we're talking about the new lambda, it's going to be 9 times the previous lambda, which comes out to 11.25. So now we got to figure out if she's going to have to empty it twice. We're going to use that new lambda of 11.25, plug it in. So I'm going to do it in R. So given that we expect her to use the jug 11.25 times on that trip, the probability of her using it 24 times and having to empty the jug twice is pretty small. I don't know. We got to change this out in the equation too. Let's see. There we go. And not going to be to the 2. It's going to be 24 uses so that it's in the same metric. Because you only have to empty the jug every 12 Ps, and we're talking about emptying it.
Why the lambda here being 1125 again?
Because we calculated it in the previous step. That's how many times she should use the jug given the 9-day trip of driving 12 hours a day.
Oh, so okay, F is after E, so that's like during 9 days.
Mm-hmm.
Okay, got it.
If this is still feeling a little weird to you, don't worry, there's another practice problem on the same sheet, and I posted this in Slack yesterday. And actually, Matt's going to show you how to do the same stuff in Python.
Yep. So if you guys want to pull up the binomial and Poisson and Python notebook, you can go ahead and dive into that. And just give me a thumbs up when you've got the notebook up. All right. Juliet, are you getting it? You're good? Okay. All right, so this is just going to be a short tutorial on how to do some of these problems in Python. It's really easy. So to do this, you just need one library. It's from SciPy, and you need the stats. Let's go ahead and run that. Wait a second. Okay. So we'll do binomial first. So the question here is, the odds of being attacked by a Demogorgon is 0.7. If 20 children run by the Demogorgon, what are the odds that exactly 15 children are attacked? So I'll give you a second to think through how you'd solve that. And then in Python, all you have to do is do stats.binom for binomial. You pass in the number of trials, you pass in the probability as the second argument. And then since we're looking for a specific value, the probability of exactly that value, we need to do PMF. So then we just do .pmf, and we want to know for 15 children. So if we run that, we get about 17.8% of the children. So, or that's the odds. So about 17.8% that 15 of the children will be attacked. So for the second question, what are the odds that between 12 and 14 children are attacked? So for this one, we do something similar. We pass in again 20 and 0.7, but this time, since it's an interval, we need to use CDF. And since it's between 12 and 14, you have to first find for 14 and then subtract for 12, and that will give us the interval in between. So if we run that, we get about a 36% chance. All right, on to Poisson. So 5 portals to the upside down opens up every hour. What are the odds that 7 portals open in the next hour? So for this, we just do stats.Poisson. And we pass in the lambda, which is 5. And then we're looking for a specific value of 7. So we do PMF. We pass in 7. And we get a 10% chance.
Hey Matt, can you explain this this Poisson function here? So 5 will be the lambda, and 7 is the k.
Yep.
Okay, thanks.
Yep, and then for the last problem here, what are the odds that 4 or less portals open in the next hour? So for this one, it's similar. We just have to use CDF. So again, we pass in the lambda, and then for CDF, we pass in 4 because we want to see for 4 or less. We run that, and it's about a 44% chance.
CDF.
So there's that. Does anybody have any questions on this?
So if you dot PMF, it will give you the probability of that event happening, right? If you just use CDF, it will give you the cumulative function.
Right, so PMF is for like an exact value, and then CDF is cumulative. So whatever value you pass in, it's that value and less.
And you can find most distribution in stats package, I guess.
Yeah, so if you do stats, and then I don't know if it'll pop up here because I'm, oh, there we go. Can you guys see that? So like there's Bernoulli, there's going to be normal, which we're going to go over tonight. Basically every distribution you could want is probably in here.
Oh, wow.
I'm actually pretty impressed. It actually has the Erlang distribution.
Yeah. I don't know what that is, but yeah.
It's a gamma where they're all exponentials with mean equal to 0. You'll find out what that means here in a little bit.
All right, so with that, we're going to move on to the continuous distributions student notebook to start the material on continuous distribution. So just give me a thumbs up when you have this open. All right, so to start, we're just going to import the libraries we're going to use. And so just to kind of recap what we did Monday night, these are the graphs that we made. So this is for 1 dice roll, 2, and 3, the sum of the rolls. So the top row is the PMFs, the bottom row is the CDFs. So you can kind of see how the distributions change as we go from 1 to 2 to 3. So now what if we have a hypothetical dice that has an infinite number of sides? This is kind of what I imagine it looking like. It couldn't exist, obviously, because you can't have an infinitely number-sided thing, but we're going to pretend it does exist. So what does that mean? That means we have a dice that could give us any value between 1 and 6. So for example, we could roll it and we could get a 2 exactly, or we could get a 2.1, or we could get a 2.0001, so on and so forth. So there's infinite possibilities we could get. So with that in mind, we're going to make a function here to let us roll this hypothetical dice. So for this, we use a uniform distribution from 1 to 6. So basically, this will give us a random floating number between 1 and 6. And then if we go ahead and roll it here a couple times, we can see we just get a bunch of random numbers. All right, so we're going to start with one die roll like we did before. Yep, uniform distribution just means it's an equal chance for all possible outcomes. So we're going to start like we did before, one dice roll. So this is going to do that 100 times and create a list of 100 dice rolls from this infinite dice. And then we're going to do what we did before and kind of count up the occurrence of all those dice rolls. And we'll see that we have a really long list, and basically all of them only happen once because there's just so many. So how could we calculate the probabilities for all the possible values in this interval? Well, the probability of each value is actually 0. Since there's an infinite number of possible values, if you do 1 over the number of possible values, 1 over infinity is basically 0. So this will just create an array of 100 zeros because that's all of our probabilities. So yeah, the probability of a continuous random variable at any specific value is 0. So then if we try to plot this, we see we just get a straight line. So plotting a PMF like we did before with the discrete dice doesn't really work. So we can instead use a distribution plot. So this is from the Seaborn library. It's a distribution plot. It's kind of like a histogram, but it will add a curve over the graph too. So now we can see the shape we would kind of expect for this, for the values between 1 and 6. And we can see it broke it down into different bins here, giving it like the histogram shape. And that allows us to show the distribution for it. So now let's do this for 2 and 3 infinite dice, rolling them and adding them together, so doing the sums. So this is just doing that, the first for 2 dice rolls and then the second for 3. So then we'll just go ahead and plot those with the probabilities, and again, they're all 0, so that doesn't really tell us anything. So we can do distribution plots again for each one. And now we see graphs that we would expect. So this first one kind of looks like our graph for the discrete dice rolling it twice, and the second one kind of looks like for the normal 3 dice rolling it 3 times. So now we're going to increase the number of rolls. So instead of doing 100, we're going to do 10,000 rolls for both 1, 2, and 3 of these infinite dice. And we're going to look at some distribution plots for all 3. So for the first one infinite die, now we can see it really is starting to resemble that distribution for just one normal die. And we're going to see something similar for 2. It's getting that like triangle shape. And for 3. And then just to kind of compare, here's the PMFs at the top for the discrete dice, and then our distribution graphs for the continuous dice with 10,000 dice rolls. So you can see with more and more rolls that we add to it, more and more samples, we approach that curve that we're expecting. So plotting CDF for a continuous random variable, you basically have to use histograms to bin the continuous values. So you have to, even if it's a large number of bins, like 1,000, 10,000 bins, you still have to do that in order to build a CDF. So we're going to do that here. NumPy has a histogram function, which basically we pass in our dice rolls, we choose a number of bins, And then it gives us the counts for each of those bins and then the intervals in which each of those bins lie. And then we can calculate our cumulative probabilities using those counts and using the cumulative sum function from NumPy. And then we'll just go ahead and plot our different intervals and the cumulative probabilities. And so this is for one dice roll. So it's just kind of a straight up line, what we would expect. It's about as likely for each value as each other. So that's kind of what we would expect there. And then this is for two dice roll. So we can see it kind of has a curve to it. And then similarly for three, it has even more of a defined curve. So now if we compare these to our discrete dice and their CDFs, we can see that again, as we have a ton of samples of our continuous variables, it approaches the curve that we would expect. So now consider rolling 100 infinite dice 10,000 times. So we're going to roll our dice 100 times per trial and add all those together and store the sum for each one. And then we're going to plot it using a distribution plot. So now we can see we have a really distinct defined curve here, which looks kind of like a normal curve. So then we can do the CDF for this 100 dice roll too. We can see that we get this nice S-shaped curve. So this kind of goes into the central limit theorem, which we're actually going to go into a lot more depth tomorrow, but this is just kind of a brief introduction to it. So one part of it is that the sum of a large number of random variables will be approximately normally distributed, regardless of the underlying distribution. So you could see as we added more and more dice, the curve of the sum of those dice rolls became more and more like a normal curve. And if you notice that last part there, regardless of the underlying distribution, we're going to kind of look at what that means now, considering a loaded die.
I have something to add here.
Sure.
It's important to note that you'll see more tomorrow, but the distributions don't magically become normal, but their summary statistics begin being distributed normally. We call that like the sampling distribution of sample means. And if we were to take the average number, like we're going to roll 10 dice, what's the average thing that we see? And then we did that hundreds of thousands of trials, the distribution of their means would be approximately normal. That doesn't hold true for variances or even for the raw data per se. And it definitely doesn't, it's not equal. So sometimes in social science textbooks, you'll see that the magic number is like n equals 30. In some jankier source distributions, you might need to look at more like n equals 3,000 before the means begin to be distributed normally. All right, thanks, Matt.
Yep. Okay, so now to explore that underlying distributions part, we're going to consider a loaded die. So this die can only be a 1, 2, 3, and then the values 4, 5, and 6 are all going to end up being 6. So you could think it has a weight in it, and it basically ends up on 6 most of the time. So that's our loaded die. So if we do one roll of that 1,000 times and then plot all of those rolls, we can see this is the distribution plot we get. And we can see that it's clearly not normal. You have a big spike at about 6, and then values 1, 2, and 3 have kind of a smaller spike. But now we're going to do 10 rolls of that loaded die and calculate the sum, and we're going to do that 1,000 times. So now we see that the sum of those rolls starts to approach a normal curve. So what is the normal distribution? Well, this is what it kind of looks like in general. The shape can be stretched more tallly, or it can be spread out more widely, but this is generally what it looks like. And on the y-axis, you'll note is probability. So normal distributions have a few properties that are important to know. The first is that the mean, median, and mode are all equal. The second is that the area under the curve is equal to 1. This makes sense since we're measuring, it's a measure of the probabilities, and probability always has to equal 1. So that's kind of why that is. Another property, which is useful, is that 68% of the values on the normal distribution are 1 standard deviation away from the center or the mean. 95% are within 2 standard deviations, and 99.7% of the values are within 3 standard deviations. And then lastly, any normal distribution can be found with just the population mean and the variance or standard deviation. So here's kind of a chart that shows those percentages. It kind of breaks it down, so like on both sides of the mean. But if you would add like the red parts together, that would equal about the 68%. And those are kind of approximate because you can see here like it's 34.13, so it would actually be a little bit over 68 if you added them together, but it's just a rough estimation. And then here's kind of showing how normal distributions can look differently. These are all normal distributions, but they have different means and different variances or standard deviations. So we're going to try and solve a problem now with this information in mind. So
Wait, before, can I ask a question?
Sure.
So in my mind, or like before I learned normal distribution is more like the frequency of or the probability of event happening, right? So if you like if you have a lot of P's and like P's and you let them drop, and then they will like accumulate as a normal curve. So that's more like a frequency, describe their frequency. So, but when you talk about central limit theorem, you actually add them together. So how, I feel like this is a different concept, how you connect them together, or can you clarify?
Sure, so let me go back actually. Let's see here. Okay, so here I calculated the sum, but it might make more sense if I ended up doing the average. So if I had divided, actually I probably could just do that here. So give me
Or can
one
you do the
second.
count, like count?
Well, so if I do the average, that mean, let's see. Or wait, what do I want to do? No, I just want to do this divided by 10. So np.divide, I just want to do all of this divided by 10. Or yeah, 10. Why is that not working? I need to, there we go. So now it's the average of the rolls. So this is kind of more what the central limit theorem is talking about. The mean approaches a normal distribution. So now this is the mean dice roll that we get. Does that kind of clarify?
Yeah, because if I think about the sum, it may be like is how to say is more I don't know, the variance may be smaller, or is more, I don't know. Like the bale is sharp, like taller, I would say.
You mean like before it was? Like if I take this away? Like it's a little more pointed this way?
I think I get it now. I just don't know how to describe it.
Aubrey, do you have anything to add on that?
I do. So in distribution theory, if you ever sum together sample statistics, the sample total is a sample statistic, the mean is a sample statistic, even the median is a sample statistic.
Mm-hmm.
If you sum them together, assuming that the underlying distribution is normal, the sum of those statistics will be normally distributed. So
Right.
if you have 100,000 sample totals, their standard deviation is going to be in keeping with the normal shape. Now, it might be a tighter distribution as you keep going than your original normal distribution was, because you've resampled and resampled and resampled, and higher n tightens up your distribution, but it still will be approximately normal. But if you
So the
add,
underlying assumption is the population follows normal distribution.
if it's nicer if it does, but if you sample enough sample means, eventually the sampling distribution of sample means will be normally distributed. And that's going to happen faster if your underlying distribution is normal. If it's something extremely left skewed, you're going to be sampling forever before the sample means begin to look normal.
Can I jump in with a real life example?
Mm-hmm.
Yeah.
Kind of going back to what we were talking about at the very beginning before we started working through all of this, like diseases in people, right? So if I'm testing for a disease in a person and I know that it happens about 10% of the time, I want to test probably like 100,000 people, but I'm not going to test 100,000 people all at once. That's insane. So I'm going to distribute that out to little labs and they're going to run their own testing, right? So they might test 1,000 people and now I'm testing 1,000 people 1,000 times. So I have like one group of 1,000 is going to have data that looks a certain way. Let's assume that it's normally distributed. Then I might have another set of data from a different lab that's like skewed right because their population is different and that population has a different rate of catching the disease. And then I have another lab and their data might be skewed left because, again, different population makes up that sampling group. But whenever I distribute all of the whenever I compare all of the summary statistics and I run my distribution stuff on those summary statistics, they will look like a normal distribution because I've done it so many times. And that's kind of what central limit theorem is talking about, is that whenever you do something so many times, it'll approach like this, I don't want to use the word constant because it's not constant. It's like this idea. They kind of come together to create this idea that we can rely on that'll happen over and over and over again. Does that make sense?
Mm-hmm.
And the underlying population is not going to become normal because you sample it, but just the sampling statistics, except for variance, because the sum of variances becomes chi-squared, as we're going to see here in a little bit. Like a peanut butter and jelly sandwich, you plop it over and then all the PB and J is on one side, the positive half of the line. I don't know, this is the sexy part of stats and I love it. Getting pretty excited.
Me too. I love it.
All right, so are we good there? Bonnie?
Yeah.
Good, okay. And yes, so tomorrow the lesson's going to be all about central limit theorem, so we'll go into in a lot more depth then. But let's see. All right, so to do a problem involving normal distributions, a radar is used to measure speeds of cars on a highway. The speeds are normally distributed with a mean of 60 miles per hour and a standard deviation of 10 miles per hour. What is the probability that a car picked at random is traveling 45 miles per hour? So to do this in Python, like we did with the binomial and Poisson, we can just do stats.normal. We pass in the mean and then the standard deviation. And then we were looking for the specific, the probability that they're going 45 miles per hour. So we do PDF. And notice it's PDF now instead of PMF, because for continuous distributions, it's density instead of mass. So if we run this, we'll notice it is a 1.29% chance that they're going 45 miles per hour. So now what is the probability that a car picked at random is traveling 45 miles per hour or less? So similarly, we passed in the mean and the standard deviation. And then this time we have to use CDF because we're looking at a value and below it cumulatively. And we pass in 45 there, and we get about a 6.7% chance. All right, another question here. Assuming a normal distribution, if 95% of data scientists drink between 7.5 and 15.5 ounces of coffee a day, what is the mean amount of coffee drank by data scientists, and what is the standard deviation? So to answer this, we need to kind of think about some of the properties of the normal distribution. So the first is that this 95%, if we remember from a few slides back, we know that that means it's 2 standard deviations away from the mean. And then the other thing, the normal distribution is symmetrical. So if both of these values are on opposite sides of the mean at equal distances, we know that the mean is just exactly in the middle. So we can find the mean by just adding these two together and dividing by 2. So I think we'll do that here in the next part here. So the mean is just the 2 intervals on either side divided by 2. That gives us the middle point, which is 11.5 ounces. And then using that mean, we can calculate the standard deviation since we knew that that interval was 2 standard deviations away. So we could take either the upper or the lower value. We'll take the upper one here. We subtract the mean from it to get that distance to that upper value. And then we know that distance is 2 standard deviations away. So we just divide by 2. And that tells us that the standard deviation is 2. So now to check this, using that mean and standard deviation, we'll check that indeed 95% of data scientists drink between 7.5 and 15.5 ounces of coffee a day. So we're going to use our stats.norm like we did before. We're going to pass in our mean of 11.5, our standard deviation of 2, and we need to know the interval 15.5 and 7.5. So we'll have to first find the CDF at 15.5 and then subtract the CDF at 7.5. And that gives us about 95%. So that kind of proves the whole 2 standard deviations is about 95% thing. All right, now we'll talk about a specific normal distribution, the standard normal distribution. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. So we can convert any normal distribution to a standard distribution with the following. We just take all the values and we subtract the mean, and then we divide by the standard deviation. And this is also the formula for calculating a z-score. So it kind of can put 2 different distributions on the same scale so that we can compare them. So that's what we're going to do here in another exercise. So considering 2 stocks, stock A and B, in terms of closing price over the last couple of years, stock A has had a mean price of 12.75 with a standard deviation of 1.5. And stock B has had a mean price of $5.30 with a standard deviation of 115. So if the current stock prices are $10.50 for stock A and $4.50 for stock B, which stock would be the better deal currently? So we want to figure out which of these current values is more below the or further from the mean below than the mean prices we have up here. So to do that, we have to, since they're in different scales and everything, we have to convert them to a standard normal distribution and basically give them a z-score. The z-score will tell us how many standard deviations a specific value is away from the mean. So here for stock A, the current price is $10.50 and the mean was $12.75. So we just plug those into the formula, x minus the mean, and then we divide by the standard deviation of 1.5. And that gives us a z-score of minus 1.5. Then for stock B, we do a similar thing, plug in the numbers, and we get a stock B score of minus 0.53. So what this tells us is that stock A comparatively is currently less than its mean value than stock B. So stock A would be the better deal there. So now using z-score when we're dealing with samples, to answer this question, the average number of scoops of ice cream sold by employees at Scoops Ahoy is 15 per hour with a standard deviation of 3. Steve worked for 6 hours and averaged 18 scoops sold per hour. What percent of employees did he do better than in selling scoops? So to solve this, we need this formula here. This is the z-test statistic formula. You'll notice it's similar to that z-score formula, except on the bottom we have the standard deviation divided by the square root of n. This basically adjusts for our sample size. So like in this case here, Steve worked for 6 hours. So that's kind of our sample size. If he worked for only 1 hour, it's kind of hard to say, you know, how much better he did. But if he worked for like 20 hours, say, then that would give us a really good idea of where his performance lies in relation to the average employee. So using that formula, we can just plug in the variables here. So x is 20, because if we go back here, let's see. Actually, I might have plugged in the wrong values. So he did 18. So this needs to be 18. And then the mean was 15. And then the standard deviation is 3. And he worked for 6 hours. So we basically have 6 samples because there's 6 hours that he worked. So if we run that, and then to calculate the z-score here, the z-statistic, we plug in these values here. So x minus the mean over the standard deviation divided by the square root of n. If we run that, we get 2.449. And so now using that z value, we can create a standard normal distribution. So this is passing in a mean of 0 and a standard deviation of 1. And then we're finding the cumulative value here at that z-score. And that tells us that Steve does better than 99.28% of all their employees. So with that, Aubrey.
What he just did there is access the quantile function. So he used the CDF command, but he's comparing it to all of the quantiles associated with varying values in that standard normal distribution, and found that he is at the 99th point something quantile. And 1 minus the quantile function is your p-value. So if we are testing at 95%, Steve has well exceeded the standard, and we would say he is significantly better than his coworkers. In fact, he even passes at the 99%. So he has a p-value of less than 0.01.
I always wondered how they figured out what percentile we tested in for like ACT and MCAT and stuff like that. This is how.
Yep, quantile function overlaid on a normal distribution.
And like height and weight when you went to the doctor when you were little. Same thing. So with all that in mind, now we're going to go into an activity. There's just 3 problems here. It's basically all the stuff we just did, except different word problems. So go ahead and give you guys some time to work on these. I'll pause recording. Start.
I hope this is right. So I had the stats norm, and then the mean was 6.45, the standard deviation was 2.35, and because we're doing like a range of numbers, I did CDF with the number that they gave us, and I got the probability of 67.
Yep, that looks good to me.
So it's 750 or more, so it should be 1 minus stats dot norm 6.45.
Oh yeah, yeah.
It again?
That's what I was missing.
Yeah, it's the inverse. So that CDF function looks at 750 or lower. So if you want to get the upper tail, you got to do 1 minus.
So 1 minus this?
It would, I would do like the whole thing you have written there in parentheses, and then 1 minus that whole thing. Yeah,
Like that.
there we go.
Yep.
And that's because we're looking for the less than.
The greater than.
I'm sorry, we're looking for the greater than, and the one that it gives it to us is less than.
Yep,
I
Yep.
got you. Okay.
good job.
All right. Who wants to do number 2?
I can try number 2.
Okay.
I'm not sure if this is correct. So to compute the mean, I use this range 32 to 48. So the mean will just be 32 plus 48 divided by 2. The mean is 40. And because this 99.7 is about like mu plus 3 times standard deviation. So, which means that that range, so if we go back here, the range will be like from here to here. So the area under green, purple, and red. So, and now I know how do I say it? So the 32 to 48 covers about 3 standard deviation from the mean. So I use, I calculate the standard deviation and is this number.
So actually, that division there you have between 48 and 40, that should be a minus.
Oh, right. This way.
Yeah.
This way. Right. Because this is 0, I don't think it's correct.
Yeah.
So, okay. This is much better. So my standard deviation is this. Thank you. And I use a stats norm. And so basically just minus the CDF of 60. Yeah, use CDF of 60 minus CDF 50. So the probability is this number.
Yep. So very low.
Yeah.
Good. All right, number 3. Who wants to do it? Beth or Jacob? Or T. Gordon, if you happen to finish it.
T. Gordon's ready to throw it on the table. I can tell from that from that username. We have a lady who stops by occasionally named Marissa, and she plays ball very strongly. I get when she comes out.
All right, can y'all see my screen?
Mm-hmm.
All right, so I did the average at 12 million for a season, standard deviation at 5 million, and Stranger Things had an average of 20 million across 3 seasons. So I just did 20 million divided by 3 and did the stats norm with the average viewer and did the CDF at Stranger Things average to see how many shows it did better than. I don't know if that's right though.
So since it's 20 million across the 3 seasons, this means that 20 million is already your average, so you don't need to divide by 3 again.
Oh. Okay.
That's looking a lot better.
Yeah.
Mhm.
94%.
Actually, so you're just plugging in the Stranger Things for the CDF, but you need to calculate the z-score first.
Oh, okay.
The probability is going to be the same because you're just scaling.
Mhm.
But yeah, the z-score is still useful
Why do I need to calculate the z-score first?
because Matt asked for it. But
Wait,
Um,
doesn't it give a different answer though?
nope.
If you plug in the z-score there, it won't.
Standard normal is just a mini version of the normal distribution, and the allocation of probability within it is the same.
Oh, sorry. I don't need to do it.
I'm confused. Can you explain again why, like in what circumstance we need to calculate the z?
Z-score is nice for when you're trying to communicate results to people. And there are many different normal distributions with lots of means and lots of standard deviations. But z-score is pretty much universally understood because it has the mean of 1 and the standard deviation of 0. So if you're trying to publish results and you say, I got a z result of 2, then somebody who does a lot of stats or somebody who's been out and about in that field is going to say, okay, well, I can reject the null hypothesis at 95%, but not quite 99%, without knowing anything about the population.
Right.
Yeah, so for this question number 3, the reason why I went to z-score first to solve it was because I was comparing Netflix to Stranger Things. Those are two different things with two different sets of statistics. So you would use the z-score to compare them in terms of each other.
You want to share your screen, Beth?
I didn't exactly get all my calculations done yet.
Okay.
Yeah, and the reason I was using it is because then I was doing like a standard normal distribution. So not passing in the mean and the standard deviation that was given, but doing 0 and 1.
Y'all got a sneak peek into hypothesis testing tonight, but we're going to have an entire episode of hypothesis testing next week. And we'll talk about when it's easiest to use Z, when it's easiest to compare normal distributions, when you're dealing with smallish sample sizes and you want to use a t-distribution, when you're actually testing variances and you don't want to use a normal-based distribution at all.
And Aubrey, I'm pretty sure it does give a different answer because that way it doesn't involve the 3 aspect, that you have 3 samples.
Did I do the score right here?
So that should be minus, yeah, and then it's the standard deviation divided by the square root of n. And you'll have to put that whole denominator in parentheses.
What's n supposed to be? The 20?
It's the
N
3.
is the number of samples, so it's 3.
Oh, okay.
So you have
And then
z-score, and then
it's a standard normal, so the mean is 1, and the standard deviation is 0. The mean is 0, and the standard deviation is 1.
Mean is 0, standard deviation is 1.
The only thing that's different is that he's adding the section for the sample size, which makes it into a hypothesis test instead of just consulting the CDF.
So the CDF here, you can put a z-score inside of it?
You could do a z-score, you could do the normal distribution, because hypothetically the z is just one version of the same normal distribution and it has the same densities. But if we're trying to ascertain whether it's statistically significant and an adequate representation of population differences, then we want to do the divided by square root of n and the sample size.
Okay.
We'll talk a little bit more about like the finesse of statistical inference next week.
Yeah, literally the content we are covering right now, it equals probably 6 hours of lecture.
That's what it feels like.
We're trying to be thorough because if this stuff doesn't land, then everything that comes afterwards is just going to be very uncomfortable.
Mm-hmm.
So the result to that was 99%?
99.7. Yep.
Because I had also done it, but I didn't do all the zeros. I just did the first like 20 and 12, and I got the same answer, and that's okay, right? Okay.
Yep.
Yep, just scaling. So yeah, tomorrow night is not Hypothalamic Thursday. We are actually going to cover the next 3 distributions, and then we're going to talk about central limit theorem. So if you can't come on Thursday, we will be recording it, but there will be some handy dandy activities for activation. So I would say come out on Thursday if you can.
Thank you.